Starting in Chapter 3, we are going to write our own proofs. In order to write our own proofs, we need to understand the information at a deeper level. We need to understand what the information implies. If we know that an angle is right, what can we imply from that information? This symbol means implies. If we know that an angle is right, what can we imply? Well, we know that if we measure a right angle, its measure is going to be 90 degrees. Think of this symbol as an if-then statement. If an angle is right, then its measure is 90 degrees. The reason for this? Well, that's the definition of a right angle. In this definition, we can look at the converse. If we measure an angle and it's 90 degrees, can we conclude that we have a right angle? Yeah. Since we can go both ways through this definition, I'm going to put an arrow on both ends of this symbol. This if-then statement can go either way. I can start with this hypothesis and conclude this, or start with this hypothesis and conclude this. Both times, my reason would be the definition of a right angle. Another piece of information. Perpendicular lines. If we know that lines are perpendicular, what can we imply? Well, if lines are perpendicular, they intersect at right angles. That can be one right angle, or two right angles, or four right angles. How do we know this? Well, that's the definition of perpendicular lines. We can start with perpendicular lines and conclude that they intersect at right angles, or we can start with this hypothesis, lines that intersect at right angles, and conclude that we have perpendicular lines. What does this allow us to do? Well, it allows us to prove that lines are perpendicular in plane geometry. In coordinate geometry, we need the opposite reciprocal. In plane geometry, we need to prove that we have a right angle. If we look at the information about a linear pair, we know that if two angles form a linear pair, then those angles have to be supplementary. What allows us to go from angles forming a linear pair to those angles being supplementary? Well, this is different than the definition of a linear pair. The definition of a linear pair is adjacent angles whose non-common sides form opposite rays. That doesn't say anything about supplementary angles. The reason that I can go from angles forming a linear pair to those angles being supplementary is the linear pair postulate. If you notice, a postulate is different than a definition. I can't start here and conclude this. If two angles are supplementary, then they form a linear pair. That is sometimes true, but it doesn't have to be true. I'm not going to draw another arrow here because I can't go both ways through this definition. But I can keep going with this definition. What does it mean to have supplementary angles? Well, that means that we have the two angles that sum to 180 degrees. How do we know that? That's the definition of supplementary angles. Can we switch around the order? Well, if I have two angles that sum to 180 degrees, can I conclude that those two angles are supplementary? Yeah. Definitions are always two-way streets. And the last piece of information we're going to look at, complementary angles. If two angles are complementary, what can we imply? What can we conclude about those angles? Well, they have to sum to 90 degrees. That's the definition of complementary angles. Again, can we go both ways through this? Well, if we have two angles that sum to 90 degrees, can we conclude that those angles are complementary? Yeah. Definitions are always two-way streets. We can imply here to here or here to here. How does this look as a proof? Well, let's look at this example. We're given that angle 1 is a right angle and angle 2 is a right angle. And we want to prove that angle 1 is congruent to angle 2. Well, this is going to be true. We need to write it as a proof. So if we look at this first given, angle 1 is a right angle. What does that imply? Well, that implies that its measure is 90 degrees. And if we look at our second given, angle 2 is a right angle. What does that imply? Well, that implies that its measure is 90 degrees. So we really have two angles that both measure to be 90 degrees. If two angles both measure to be 90 degrees, that means that those two angles are equal. And if we can prove that these two angles are equal, we can prove that those two angles are congruent. That's the basic outline for our proof. We just need to write a logical argument. Our first statement is our given. If this is true, then this is true. If angle 1 is a right angle, then when I measure angle 1, I get 90 degrees. That's the definition of right angles. My third statement, angle 2 is a right angle. That's my second given. Well, if I measure angle 2, its measure is going to be 90 degrees. Notice how this proof is written. I've taken my first given and I've concluded something based on that given. Then I've gone to my second given and concluded something about that given. I didn't just list my givens at the beginning. I used my given as far as I could go. Well, now I have two equal signs in my proof. And if I look, my equal signs both have a 90 degrees in them. Well, since they're both 90 degrees, I can substitute. And in this case, I'm going to substitute 2 into 4. So now I'm left with the measure of angle 2 equals the measure of angle 1. They're both 90 degrees, so they're going to be equal to each other. But I want to prove that angle 1 is congruent to angle 2, so I need to have angle 1 first. So I'm going to switch the order, and I'm going to flip around this equal sign. What property allows me to flip around an equal sign? Well, that's the symmetric property. Left equals right, right equals left. Symmetric. And if two angles have equal measures, then those two angles have to be congruent. If this is true, then this is true. That's the definition of congruence.